We're continuing our exploration of mechanisms, our introduction thereto. With this mechanism here, where we're taking 4-methyl-1-pentene, I can go pentuanine as well. And the two products are 2,4, no, I can't do that. 2-chloro 4-methyl-pentane. And the other one is 1-chloro 4-methylpentane. And the reaction is called, not very imaginatively, hydrohalogenation. Yeah. We're adding a hydrogen to one side and a halogen to the other. And it's done using a strong acid, isn't it? Strong acid. Can you tell me what the word strong means? Say it again. No, we have strong acids that are monoprotonated, triprotonated, tetraprotonated. It doesn't matter how many H's there are. Yes, they dissociate completely because the molecules vary. It's not stable. The opposite. What is it? Okay, she said unstable. That's a nice way to go with opposite. Good use of English there. Reactive. That's a hint how to start. HCl is a strong acid, which means it's reactive. Guess what you need to react first? It's a strong acid, okay? Some pair of electrons is interested in the proton. Why? Big reason. The proton is very positive in nature, isn't it? Bonded to an electronegative Cl. Which pair of electrons in 4-methylpentuanine is the most reactive? I need a Greek letter. Yes, never tell me a sigma reacts before a pi, but occasionally you can, but there's usually special circumstances there. This is not one of them. Pi reacts before sigma. So that's a hint how you start. Your pi electron, go right in the middle of the, make sure your arrow starts on the middle of the pi bond and ends right at the H atom. I don't like arrows starting or ending in outer space. They will lose points because arrows have to start at a pair of electrons. Arrows either, we learned in our labeling activity at the beginning, they either ended at an atom as a lone pair, or at an atom as a sigma bond, or between two atoms, and then it became what? A pi bond. Pi bond. Those are your three ends for arrows. Starts are lone pairs or some kind of bond. Lone pair, sigma bond, pi bond. If you have a choice between sigma and pi, guess which one? Pi. Why? Weaker bond. I'm like a 2-year-old sometimes. Why is it a weaker bond? And just get ready for the next why until I'm happy. Why is a pi weaker than a sigma bond? Well, they're both sharing of electrons. One of them shares a little better, but why? Sigma shares a little better. Means it's stronger. The more equal, I think we're getting closer. Equal. What do you mean by that?
Like
more covalent?
Yeah.
No, they're both covalent. They're both equally covalent because they're a sigma bond and a pi bond between the same two elements. They're the same atoms. You can't say one's more polar than the other, right? Same electronegativities are in play. where is a sigma bond? If you're an atom A bonded to an atom B and you have a sigma and a pi, where there's my hands that need a bond. Where are the electrons in a sigma bond? This is the definition of sigma bond about to happen right now. It's because of the location of the electrons that it's called a sigma bond. Where are they? Isn't that the best place for electrons? Between two nuclei. Nuclei have protons, and you're talking about electrons needing to be close to protons for stability. Isn't the best place between the two nuclei? Okay, that spot's taken because you made your sigma bond. You can't use it again for pi. Where's the next best location to make your pi? There's no bonding if you put electrons any outside either atom. That's not a bond. The electrons have to be between the atoms for bonding to even occur. Did I say it again? Parallel. I think you're getting at above and below, and parallel to that sigma you did before. I think I like that. But the fact is, it's not in between anymore. It's above and below. The pi's up here, right? Is that as close to the to the protons in the nucleus? No. So why is a pi weaker than a sigma? Because the electrons aren't as close to the nucleus because they're not directly between the two nuclei, which is the definition of sigma. Sigma has electrons directly between the nuclei. It's the only definition. Okay, so you're going to break pi first. And back to sharing and caring. Okay, now you can't just make a second bond to hydrogen and leave it like that. You try drawing two bonds to hydrogen on a test and you're going to lose a point. Octet violation. So you have to compensate by doing what? Well, tell me where your arrow starts and where it ends, because we've already seen this one. The sigma bond between H and Cl becomes a what on Cl? A lone pair. Thank you. Nicely said. And by forcing yourself to use the words, you're actually learning how to do it by hand. And I'm going to put the intermediates underneath. And what happens is, not yet. If you put the H on the right side, that means the carbon to the left of that didn't get a new bond, right? So it lost its fourth bond. So what kind of charge does it have? It's a cation. It's called a secondary carbocation. Now, if you put the H on that atom, now which carbon is lacking a fourth bond now? The primary is the carbocation. Now, you go on the weekend and you look up for the lectures that explain why secondary carbocations are a lot more stable than primary. You need to know that this weekend. I'm not going to go through that right now. There's 3 or 4 videos with that. So I'm going to make up some numbers now. I'd say roughly 80% of the cations are like this, and roughly 20% are like this, because of that stability difference. You have a choice of making things that are more stable versus less stable. Guess which ones are generally major? The more stable one, because it's easier to make. And every time you made each cation, what happened to the HCl? I know where the H went. I drew them already. What's the rest? Cl minus. To be Cl minus, I'm going to draw only one time with a full Lewis structure because that is a huge waste of time. From now on, I'm only going to draw a lone pair if I need it in the mechanism. The second one is the way you should draw it. Please don't forget that the first one is really how you get a Cl minus. If it doesn't have 4 lone pairs, it's not a Cl minus. Okay. And this is very slow. This step we just did is very slow. Maybe somebody can answer this question. Why do you think it is so slow? Generally, slow reactions make species that are not that stable. So talk to me about why these new products are not as stable as the originals. Because the carbon doesn't have a full octet. That's always going to be a slow process. Yeah, and what about another factor that's not quite as important? She nailed the very important one. There's a smaller effect here. Do you see any charges in the reactant? The top of the screen? No charges. Bottom of the screen, there's charges everywhere. What's more stable? No charge or charge? No charge. You're balancing your electrons better with your protons. Okay, so the next step is fast. Whether it's this fast step, this one goes to there, or this fast step. I wonder if I can make that work nice. That's not terrible. They're both fast. What's a good color for fast? Red? Red shadow? Fast. And how do you think it gets there? I think each product only needs one arrow. Can you tell me how that arrow, where it starts? The lone pair on Cl, and where does it end? Careful how you speak. I just want to remind you, a cation is not a thing. A carbon atom is a thing, right? So if somebody says end the arrow at the cation, you're going to lose a quarter point. That's an arrow ending in outer space. Arrows end at atoms or between atoms, right? Is it very clear my arrow doesn't end at the cation, it goes all the way to the carbon? I hope it is. Same story here. I'm not messing around. I'm going to make sure you know it goes all the way to that carbon. See that? Like touching it. Okay. Oh, good. Are we ready to get our Lubnu Habibi on? Okay, the pi electrons start the first one. So do they get the nucleophile or the electrophile distinction? The attacker is always a Lubnu. Is it attacking a proton? It better be a Habibi too. The thing getting attacked, if it's Lubnu BB attacking something, the thing attacked every time is Ilaba. So you can keep things straight. If you have 3 labels for a reactant, then the other reactant better have 3 labels. If you have 2 labels for a different reaction, then the other reactant better have 2 labels. And then you generated a carbocation that didn't get it, wasn't an attacker. So go to the Cl minus. That's the attacker in the next ones, right? Cl minus is the attacker. What does the attacker always get, regardless? Lubnu. Lubnu. Please do not add a Habibi. It does not attack a proton. It attacks a carbon. And do not go Ilaba. It's Ilab. Same over here. Getting the same points for the same labels, or more points for the same labels. We love this stuff. All right. You got no room, right? Think you can squeeze another one in there? No, I don't think so. All right, sorry. Stop the video.